In the last video, we used Lab to create a polygonal plane mesh which had specifiable user width and height that controlled the dimensions of our plane. In this video, I want to get a little bit more in-depth into the whole plane creation process and add a way for user to specify the number of segments they want in their plane. And just to make it a little bit more difficult, maybe we can add both vertical and horizontal segments as parameters. As we will discover in a few minutes, adding segments to a plane significantly complicates the process of generating it. So we will need to do some basic theory before we go on into creating the plane ourselves from scratch. Just to cover the theory, I want to go back to our Windows Paint application here and kind of draw out exactly what we are planning to do. So essentially, before, if you remember, we had a plane which consisted of 4 vertices located in 4 corners of the plane, and these vertices were connected together with a single polygon. What we want to achieve in this video is to basically allow users to add more polygons and more detail to this plane by kind of injecting segments into our plane, both vertically in this case and horizontally, just like this. There are a number of ways that we can think of doing this. The first way would probably be just taking our initial plane and thinking about it as being one of these little squares over here. So we would have our 4 vertices over here, and then we can basically take this plane and copy it over any number of times that can be specified by the user. The problem with this approach is that we are getting a lot of wasted vertices. So because you will be copying this plane over here, you will be forced to create this vertex here all over again while the previous vertex is still there. So you will have 2 vertices in this kind of intersecting locations next to each other, which isn't really ideal because it will not only allow or disallow smoothing between the two polygons, but it will also increase the amount of memory used by the plane and generally make the whole process less efficient. So what we will do instead is we will first create a grid of vertices, just like so. Let me show you on a new painting. We'll first create a grid of vertices going in horizontal direction, and then we will continue this grid on the y-axis as well until we reach our final count of vertices that we want. And we will compute this count based on the number of segments that the user specifies for the plane. So let's just say we have something like this at the end, and the way that we will number these vertices now will be starting from the top left corner. So we will number this one as 0, this vertex will be 1, this one will be 2, this one will be 3, this one will be 4, and then we will continue on to the next row of vertices. So this vertex will be number 5, this one will be number 6, this one will be number 7, 8, and so on. We can continue on until we get essentially to our very last vertex over here. And now that we start thinking about it, we can rationalize and kind of introduce some variables into this whole mix. And instead of having a fixed number of vertices, we can think in terms of having a variable number of vertices over here. So let's say that we want to have, let's put it C for columns. So C would be the number of columns that we will have in our grid, and we'll have R for number of rows. Alternatively, you can think of this as these being the horizontal segments and this being the vertical segments of our plane. So now we have 2 variables, C and R, which are specifiable by the user. And now we can say that instead of this going from 0 to 4, this kind of this array of vertices extends from 0 essentially to C minus 1. And the reason it is going to C minus 1 and not C is because we are starting from 0. So in this case, we have 0, 1, 2, 3, 4. So it ends with 4, but in reality we have 1, 2, 3, 4, 5 vertices over here. So if user specified 5 for C, our last index will be 5 minus 1, which is 4. And with the rows, same deal here. So we'll have at the end, if this is the very first row, we will have r minus 1 rows going vertically. And I'm sorry for this drawing being so rough. I'm kind of having to do it with my mouse, and this is kind of really hard to do without a tablet smoothly. So now let's redraw this diagram in terms of using C and R. And let's call this number C minus 1. Let's call this, let's define this as a new variable of W. Let's just put it or you know what, let's call it N. And N is going to be C minus 1. And let's call this one, let's introduce a new variable for this, and let's call it M. And the M is going to be R minus 1. Alternatively, you can also think as N and M as the number of actual segments that we will have in our mesh. So because we have 5 vertices, 1, 2, 3, 4, 5 here, we only have 4 polygons. So we have 1, 2, 3, 4. So we can think of N as the number of horizontal polygons, and we can think of M as the number of vertical polygons. So overall, if you're curious, we will have the total number of polygons in the mesh will be N times N. So this will be the total number of polygons total. I'm just going to clear the view so we have a blank slate on our hands, and I just discovered the type tool, which will come in very handy, and I will try to use it right now to redefine our variables. And our variables from the previous drawing were C, which was the number of columns in our polygon plane. Then we have R, which was the number of rows in our plane. And then we also created 2 variables, M, which was number of columns minus 1, and N, which was number of columns of rows minus 1. And incidentally, because horizontally we have 1 less face than we have vertices, and same thing vertically, M will be the number of faces that we will have in our plane horizontally, and N will be the number of faces that we'll have in our plane vertically. So the total number of vertices that we will have, so I'm just going to write total vertices, is going to be C times R, which is number of rows and number of columns of our mesh, and then the total number of faces, or let's call them polygons so don't get confused with the terminology. It's going to be M times N, which is the number of face rows times the number of face columns. What I want to do in this diagram is to introduce a couple of new variables. The first one is going to be I, and I basically is going to be the index of our vertex. As we start iterating from 0 to the very last vertex, which is C times R, we will enumerate each vertex using a unique integer incrementing in ones. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7, all the way until C times R. And the same thing we'll do with the faces. So I'll introduce a variable called J, which is index. I'm sorry, I promised to call it polygons, so I'll stick with polygons. So index of polygons. And index of polygons is going to be going all the way from 0 until M times N, which is our very last polygon. Well, actually M times N minus 1, because we are using 0-based indices instead of 1s. And here we'll have 0 all the way until C times R minus 1. So these are going to be all the vertices that we will have in our mesh, and these are going to be all the polygons that we have in our mesh, and we're going to have to give them unique indices based on their position. And the real question that we should be answering to write our algorithm is, given any position of our vertex, how do we figure out its 3-dimensional world coordinates, which will be the x, y, and z coordinates? And let's group all these coordinates together into a variable called v, lowercase v, and v is going to be the position of our vertex. So given I, how do we get v? So what we're interested in is getting some kind of function which creates v, and it depends on I. And the same thing we need to do for the face. For any given integer j, which will be the index of our face, how do we find out the 4 indices that 4 vertex indices that this face references? So let's call this indices f. Let's just group them together as f. And f is also going to be some function of j. So this means that we take j, we do something with it, and at the end we get f. And f will consist of Let me just write this like this. F will consist of F1, F2, F3, and F4, which are the four vertex indices for each phase. To clarify this a little bit more, because people are probably going to be confused, I will draw out the grid again. So let me just start out with the very first vertex, and then second vertex, third vertex, fourth vertex, and then we have an indefinite number of vertices. And the last vertex of this column, once we reach it, just like a typewriter, we go on to the next row and we start the vertices again. And then we have an indefinite number of vertices. We have a last vertex of this column. We go to the next row and we continue this process until we reach the user specified number of columns C and the user specified number of rows R. And this is going to be our very last vertex. So as we do this, we give each vertex its unique integer value. So this is going to be 0, this is going to be first vertex, second, third, and we will have the very last vertex of this column as C minus 1. Again, it's minus 1 because we're starting from 0 instead of 1. Otherwise, it would be C number of vertices in this column. So then the next column will start with the vertex with index C because it's following C minus 1. It's going to be C plus 1. It's going to be C plus 2. There's going to be C plus 3 and so on. And the total number of vertices or the last index of the vertex in this column is going to be 2C minus 1. And again, this basically means that we had C vertices before, we added another C vertices, and we're subtracting 1 because the very first index was 0, not 1. And we'll continue this process along. So this is going to be 2C plus 1 here. It's going to be 2C plus 2. It's going to be 2C plus 3, and so on until we get 3C minus 1. And then this is going to be our very last row. And the very last index, as we have established before, is going to be RC or CR minus 1, which is our index of our very last vertex. So let's think a little bit about how we can take any one of these random indices at random, and how can we extract the x, y, and z coordinate for this particular index. Well, we shouldn't really worry about the z coordinate, as you remember from previous videos, because we just have a two-dimensional plane. Our z will always be 0, so let's just delete it. So what about x and y? How do we calculate x and y positions? Well, as it turns out, that it's pretty easy, because all we need to do is for any given vertex index, we need to figure out which column this vertex is positioned on, and this is going to be our x-coordinate. Then we need to find out which row this vertex is positioned on, and this is going to be our y-coordinate. And to find out the value to find out the index of the column of our vertex, all we really need to do is find out how many columns, how many total vertices per column went into this index. So our index, let's call it vertex row. Let's start with the row. So vertex row index is actually going to be any given index I. We're going to take I, and then we need to find out how many columns went into this index. So this means that we have to divide I by C, which is the vertices per column. But then we're going to get some kind of a decimal fractional number. And we're not really interested in the remainder of this number. All we're interested in is how many whole columns went into it. So we need to get just the integer part of this result. And this is going to give us our row number. For column number, which we'll mark as lowercase vc, we need to do the same thing, except now we're not really interested about the row which it is on, but we're just interested in the remainder part after we take the whole number of rows. So think about it as here, for example, we just need to remove C from all of this row. Here you need to remove 2C, and we're just left with 1, 2, 3, 4, 5, which is exactly what we're looking for, which is our column index. And to get the remainder of this division, there is a handy function in programming called modulus. And basically modulus, or mod for short, allows you to take an index I divided by some number, which is in our case EC, and it is just going to return to us the remainder of this division. It's not going to return to us the whole number part of this division. So there we have it. Now we have the row index of any given vertex and column index of any given vertex just by using its enumerated index and using the total number of vertices per column. And our x value is going to be some kind of multiple of this. So our x value is going to be our column number times some kind of value which will indicate how much we want to expand or stretch our plane. So we'll just call this value our width, but in reality we'll probably need to modify the width to make the plane, constant. So the width is along the whole column as opposed to from one vertex to another. And the same thing is for y. So y is going to be our vertex row times the height of our plane, which will stretch it or compress it based on the user specified parameter. So there you have it. You have the x and y parameter, and now we can jump onto the faces. So for the faces, as you can recall from the previous video, we are joining our vertices together just like this, and we are doing so in a either clockwise or counterclockwise manner, but we never do it in a zigzag manner because we're interested in specifying faces in kind of a rotational circular way. So in this case we draw a face like this, and then we jump over to the next vertex and we create another face. Then we go to the next vertex, we create another face between these four vertex indices, and then we create another one, and then we create the very last face of this column. Once we do that, just like with the vertices and typewriters, we jump over to the next row, we create a face here, and then we keep going to face here and face here and face here, and we keep doing this process over and over again until we reach the very last face, which is going to be at the bottom corner, and it's going to be touching our very last vertex over here. Just like with vertices, we're going to be assigning indices to each face. So this is going to be index 0, this is going to be 1, this is going to be 2, and the very last face in the first row is going to be m minus 1, just because we have m faces and we're also starting at 0, so it's minus 1. So the next row will have face number m, face number m plus 1, face number m plus 2, and it's going to go all the way like this until we reach the very last face, which, as we discovered, is m times n minus 1. So for any given integer, so all of these integers, all of these indices are actually index j, which is index of our polygon. And for any given index j, how do we figure out the four f1, f2, f3, f4 indices of vertices that go into this polygon? And to answer this, we really need to figure out the index, the column, just like for the vertex. So first need to figure out the column and row index of each face, judging by its overall index. And just like vertices, we can repeat the same process as we did here, except we need to substitute c for m, because now we have not c many faces, but m many faces per column. And we will get our face. So let's call it fr for face row index is going to be integer part of j divided by m. And our face column is going to be modulus or remainder of j division by m. So now we have the column and row index of each face, and judging by this, now we can kind of think about how we can extract the four indices for each vertex. And to make it simpler, let's kind of write down what would be the four indices for the very first face. So face number 0, indices are 0, 1, c plus 1, and c. So 0, 1, c plus 1 plus c and c. Face number 1 is going to be incremented by 1. So we have vertex 0, vertex 2, c plus 2, c plus 1. And let's just jump to the next row to keep it shorter. So face times face m is going to be c, c plus 1. Then we have 2c plus 1. And then we have 2c. So let's start thinking about how we can extract our very first vertex index based on this pattern. And and in reality, the very first vertex index will be our face number. So it's going to be, let's just type this, face vertex index number 1. It's going to be our face row number times the number of vertices we have per column times C. So for example, for the very first face in each column, this is going to be 0 times C, so we get 0. It's going to be 1 times C, we get 1. It's going to be 2 times C because this is the second row, so we get 2, and we keep going like this. But then we also need to add the horizontal offset for each one of these faces, which is our column index for the face. So we add FC. So for example, here we get 0 times C plus 1, which is the column index of the face, row index times C plus 1 here, and we can keep going like this for any given configuration. So face index number 2, face vertex index number 2 is going to be basically face vertex index number 1 plus 1, because we are always going to use the very next following vertex for the second vertex. So this one is very easy. The vertex index number 3 is going to be, we can think about it as taking this second vertex index and offsetting it down by 1 column. So we need to take F2 and basically add a column to it. So it's all going to be F2 plus number of vertices per column. And the very last face vertex index is going to be F3, because we just basically take the previous index and we subtract 1 because we have the preceding vertex here. So it's F3 minus 1. And there we have it. We have our 4 face indices, we have our vertex coordinates, and we have our terminology defined. So I think at this point we're ready to jump into the lab and start creating the algorithm which generates our final plane. So I'm just marking the important parts here. This is the face index. These are our vertex indices, and again, this is how we find the column and row indices for each face. And this is just some of our terminology which we will use. I want to keep the video short, so I'm going to leave the algorithm off to the next video.